So proof of stake and the next generation of Ethereum. So our agenda is, we'll start with a short introduction, talk a little bit about proof of work and proof of stake in a very high level. And then we will visit PPCoin, okay, which was the first system to incorporate proof of stake. Okay, will be a case study. And from there, we will understand the challenges in implementing proof of stake systems. And we will cover a few of those in more detail. And then we will move to Ethereum and Casper FFG. Great. So I think the first question that should be asked is, why is proof of stake interesting today? Why now? So I think the main reason is Ethereum. Ethereum is the second largest cryptocurrency, right? It holds around $60 billion. And Casper, it's their code name for their aspirations to migrate from proof of work to proof of stake. And this project, this really big project, Casper, is becoming a reality. An alpha testnet was launched 5 months ago. First testnet version from a month ago. And there are serious voices about mainnet implementation from Vitalik, and who is running this project. Okay, other projects in the field. So we have EOS, right? EOS has just launched a mainnet, DPoS mainnet, 21 block producers. There was a big, talk on Twitter. It was good, it wasn't good, I don't know. We have Cosmos, we have Thunder Token, which is a project by Elaine Shih and Rafael Paz from Cornell. We have Algorand, which is Silvio Micali's project, okay? Definity. So many big projects are, and smart people are working on proof of stake. Okay, so what is proof of stake in a very kind of high level? I was looking for a good definition. I think this kind of covers what proof of stake tries to be. So in a proof of stake system, a blockchain appends and agrees on new blocks through a process where anyone who holds coins inside of the system can participate. So you want to participate in the proof of stake system, you need coins in the system. And the influence an agent has is proportional to the number of coins or stake it holds. Okay? If you have more coins, you are more powerful in the system. This is a vastly more efficient alternative to proof of work mining and enables blockchains to operate without mining's high hardware and electricity costs. Great. Who said this? Anyone knows? I guess. Huh? Nobody? No, not Satoshi. Vitalik. Okay? So Vitalik said this, right? And it's not by chance that he says, in the same breath that he says proof of stake, he says proof of work. Okay? If we look at when proof of stake was conceived, when the idea was first mentioned in the public domain, so it's in this blog post from July 2011 on the Bitcoin forum from Quantum Mechanic, an anonymous user who said proof of stake instead of proof of work. Okay? So the idea was born by looking at Bitcoin and looking at proof of work. And as Vitalik says, we want a more efficient alternative to proof of work. Okay, but what's so good about proof of work anyway? Why do we like proof of work so much? So let's look at it from the miners' point of view. So the miners, when they look at Bitcoin, what do they see? They see an ongoing lottery, right, that distributes around $15 million US every day. And if you want to participate in this lottery, you need to buy a ticket, and a ticket is a SHA-256 computation. And what is really nice about this proof of work system is that the more tickets are bought, the more secure the network becomes. And let me just show you this link really quickly. So what we see here is how many tickets basically are being bought for this lottery every second. So right now we are at 35 million terahashes tickets per second. Okay, so this is pretty amazing. If you were to compete with the Bitcoin network, you would basically need to compute 35 million terahashes per second. And if you do a quick calculation, you take the strongest ASIC there is, which does around 14 terahashes per second, then you reach this amazing number where you have 2.5 million ASICs that you need in order to compete with the Bitcoin network, which is, we did a calculation, it's around $60 billion, okay? So the Bitcoin network is very secure. And, okay, but what are we securing exactly? So what are we securing? What Bitcoin or other proof-of-work blockchains maintain or secure, they're maintaining a state under consensus. So think about it as a database that is kept in consensus between all the participants of the network, and no one can, play with it, alter it, tamper with it, manipulate it, and this is what it secures. Basically, there are operations that you can do in order to change the state, and Bitcoin uses this to do a peer-to-peer currency, basically. And Ethereum, he has a more general state. There are more operations that you can do in order to update the state. But the concept basically is the same. And the amazing thing is that it's pretty easy to get secured systems. But this system, you don't need to trust anyone. Okay, there's no one person that runs this database. The database is run, on tens of thousands of servers or computers. And as a user, when you want to interact with the system, you really don't have to rely on anyone, or you don't have to trust anyone. Okay, this is pretty amazing. And let me just show you a quick illustration to Bitcoin's power and to the amount of trust that we put in the system. We don't put it in anyone in specific, but we put it in the system. So this is a nice website that shows the transactions in the mempool. So these are people that are trying to move money around on Bitcoin. And I hope this doesn't disappoint us, but generally, if you look at this for about a minute, you're going to see a pretty big transaction in the hundreds of thousands of dollars. So people trust the system in the amount that they would transfer these big amounts over the Bitcoin network. And let's wait one more second. I hope it comes. Okay, this is live, right? So I might not happen. Last time I did it, we saw 1.5 million. Okay, so here is 112. Here is 228. So it's pretty amazing that people trust the Bitcoin network to store their money. And I think it's not that, I don't think people would disagree so much if I were to say that it's probably one of the safest places to store your money, right? Not the value, because the value fluctuates very, all the time, but if you want to make sure that your money is not stolen from you, it's probably a better alternative than cash, right? It's probably a better alternative than the bank in many countries around the world. And generally, it's a pretty secure system. So I hope I convince you that proof of work gives us security over a state, over a database. Okay, but proof of work has many disadvantages, and this is why we need an alternative. This is why we want proof of stake. What are the disadvantages? So the environment doesn't like Bitcoin so much because of the electricity. People compare it to Ireland in terms of electricity consumption. Proof of work pays a lot for security, okay? Either by fees or by inflation tax, but it doesn't matter. All this electricity goes to security, for the security of the system. Another disadvantage is that mining can be an unfair competition, okay? So if I were to develop a much better ASIC than anybody else, then the game of mining is all of a sudden not fair, and I have a huge advantage over everybody else. Electricity costs, if I live in a country where electricity is cheap, again, I have an unfair advantage. If I live in a cold place and I need to spend less money on cooling my hardware, again, an unfair advantage. And software like ASIC Boost, right, that smart people come up with these algorithms to accelerate their hash rate by 20%, and they all of a sudden, again, get an advantage. So just a question, how would this be better in proof of stake? What is the analog in proof of stake to the mining power? What do you need? You need coins, right? You need coins. And I know the price of the coin in the market, so it becomes more fair, probably, right? Because I just need to buy those coins somehow, and in order to get power. So I can't come with this trick, with this ASIC boost, and all of a sudden get an advantage. Okay? And then another thing I want to mention here is mine hopping. Okay, in Bitcoin, in miners, in the different blockchains, what they do, right, is they hop from blockchain to blockchain. They want to maximize their profits, and this kind of creates fluctuations in the security of the networks. What is the analog of this in proof of stake? Yeah, you go to an exchange, buy different tokens, but as we will see later on, it's going to be a little bit more difficult with proof of stake to exchange stake in the systems very fast. Okay, we'll see that in a second. Okay, so proof of work can be described with a three-element feedback loop. We have the miners, they join the lottery, they buy tickets, they make the network more secure, they make the network more secure, the value could go up, the value goes up, more miners join, and this goes on and on and on. And this is great for security, but it's bad for the environment, right? Because of all the hash computations. So what do we want? We want a proof of stake system where security is bought cheaply, okay? And the way you would do that is somehow design a system where if the value goes up, the network becomes more secure. And then the value can go up again. And this is something that we're trying to build. Okay, so we said an alternative to proof of work. So I'm not going to explain further how proof of work works, but let me just point out really the critical elements in proof of work that make it so powerful. So the first thing is leader election among a dynamic set of anonymous candidates. Okay, so what proof of work gives us is we have this set of candidates. You can join or leave as you wish. They're anonymous. We don't know who they are. We don't care who they are. And proof of work magically elects one of them and tells him, okay, you propose a block now. And this random election is weighted according to the amount of work that this candidate is doing, meaning to the amount of security that he kind of gives the network. Okay? And the random election is unpredictable and it's non-manipulable. So if I'm a leader now, if I was chosen a leader now, there's nothing I can do to increase my chances of being a leader again in the future. And we have rate control, right? We can kind of control the rate in which leaders are being elected. And then there's a chain selection rule, the longest chain. But there's also a coin distribution mechanism that incentivizes miners to join in the first place, but it also incentivizes people to follow this chain selection rule. Okay? So if I want to be rewarded for my work, I have to follow the chain selection rule. And let me sum the introduction up with another quote that I like. It says, proof of work follows the principle of making history costly to create and rewarding participants that contribute to its majority version. Okay? So if you're able to write history, which is costly, and you want to get a reward for your work, you would have to contribute to the majority version and not to some other version that you like or for some reason, okay? So back to the agenda. Any questions till now? Okay, great. So this was nothing new, right? And we're moving on to PPCoin, and we want to analyze the system, okay? So this is a link to the white paper. And PPCoin was the first system to incorporate proof of stake. It was launched in 2012, so about 6 years ago. It's not a pure proof of stake system. It's a hybrid proof of stake, proof of work system. So there are proof of work blocks, and then there are proof of stake blocks, and then more proof of work blocks, and more proof of stake blocks. And the basic motivation of the authors of, or the the designers of the system was that eventually, the block reward in Bitcoin and in other blockchains will disappear, or will be very, very small. And at that point, miners will have much less of an incentive to mine blocks, or the fees will become very, very high. So we need to come up with some way to produce blocks in a cheap way, okay, so that the fees could be kept low, but the chain would continue, okay? And then they invented this concept of coinage that we're going to see in a second. Okay, so proof of work blocks are completely identical to Bitcoin, and proof of stake blocks are a little bit different. So if you want to mine a block, proof of stake block in PPCoin, you need to satisfy this formula, okay? And this formula seems a little bit complicated, so we'll break it down. So let's say the state of the blockchain is, the current UTXO set and the clock. And you ask yourself, can I build a valid proof of stake block now? Okay, great. So what you need to do is first, okay, I emphasize that there's no nonce here. So there's nothing that you can kind of iterate over very quickly or anything like that, okay? Okay, and so the first thing that you do is you pick a UTXO that you own, okay? And you get one attempt per UTXO where the UTXO is weighted, okay, can you see this? Yeah. Is weighted according to the amount of coins in this UTXO and the amount of time weight of the UTXO, which is the time that this UTXO exists. And this is the coin age of the UTXO. Yep.
What is a nonce and what is UTXO?
Okay. A nonce is a random number that just gets incremented all the time. This is how proof of work works in Bitcoin. UTXO is, think of it as a coin in the system. Okay, so you have a coin, it has a value, and it has a time when it was, created. Okay, you get one attempt per UTXO, okay, and it's weighted according to the coin age of your coin. And you get one attempt per second. You see the time in seconds, okay? You don't have that many attempts. You get only one attempt per second, okay? This is, remember the terahashes of attempts you get in Bitcoin. Here you get only one, okay? And D is a difficulty parameter just as in Bitcoin. It should, should give us rate control. And then this weird prev blocks data field, which what it should give the system is the ability is to make sure that the leader that's being elected now is being elected in a non-manipulable and an unpredicted way. Okay, so you want nobody to have the power to control this data field and in that way increase its chances of being elected as the next leader. Okay, and we will see that it's very hard to come up with the correct field here, and we'll see that in a second. But if so say you have a UTXO, and the time comes, and you satisfy this formula. So what you do, you basically spend this UTXO, and you consume the coin age of this coin, right? And you put this into a block. We call this transaction a coin stake transaction, similar to the Coinbase transaction in Bitcoin. You put this into a block, and you publish the block, and everybody can verify that the block is valid, and you satisfy the formula, and great. Okay, so what are the challenges with this system? So how do we make sure that the leader election is actually random and it's fair? Okay, so this prev blocks data field should help. This is what he's for. And so let's try to find the right one. So attempt number 1 would be, let's just not have it. Let's have it blank, okay? So if we have it blank, what happens? Everybody can basically see into the future. I have a UTXO. I have the clock. Let's run the clock forward and see at what time I will be able to be the leader and propose a block to the system with my coin, with my UTXO. So seeing into the future is one problem that we don't like so much. But then this becomes even worse because I have a UTXO and I can always kind of say, okay, but if this UTXO was a little bit different, okay, if I change something in it, will I have to wait less in order to find a valid block? And then what I would do is I would start tweaking my UTXOs, right, until I find a great UTXO that gives me, that makes me the leader really, really soon. And I would just publish this transaction that consumes the old UTXO to the new UTXO, and boom, I could be the leader very quickly. Okay, so this becomes kind of like a fancy form of proof of work where you have to find the right UTXOs. Okay, the second attempt would be, okay, let's use the previous block's hash. Okay, this is a pretty natural choice. But again, if I'm the leader now and I get to choose the block, then I can also see if I get to be elected as a leader soon after I propose this block, right? I can kind of run time forward and see if I get to mine a new block soon after the one that I just proposed. And if this happens, then great. I know that I'll be the leader twice in a row. But if it doesn't happen, then we're back at proof of work, because what I'll do, I'll just change my block a little bit such that its hash will change a little bit, and then I might be elected as a leader. So I just tweak my blocks, keep tweaking my blocks until I find the right block, and I would then publish it. Okay, worse than that, I could build these long chains, these long hidden chains like this, and then I could double spend pretty easily. So these systems, as you see, are problematic in terms of security. The third attempt would be use the last proof of work block's hash, and so we're kind of losing the edge, right? We're relying on proof of work again, and we can see into the future up to the next proof of work block, which could, I don't know when it will be, but still, if it takes a long time, then I might be able to have a few blocks in a row and try to double spend like that. Okay. So we understand that it's difficult to come up with a formula that will guarantee that the random election of the leaders is fair. Okay, second challenge is what we call rational forks. Sometimes it's called nothing at stake. That's the more popular name for it. And so let's see what this is all about. So let's start with proof of work. Okay, in proof of work, what happens? We have this chain. The chain grows, and everything is great. And then I ask myself, do I have a valid proof of work now? Okay, can I propose a block now? And I get a reply immediately. I get a yes. I publish the block. I'm happy. If I get a no, I have to increment the nonce and try again, right? And we said if I'm a pretty strong miner, then I get, I don't know, maybe 100, 200, maybe 1,000 terahashes, million terahashes per second of these trials, okay? And then if a fork arrives, I have no more compute resources that are available, that I can do anything with them. So I have to choose. Either I work on one chain, on one fork, or I work on another fork, or I split my resources half-half, or something like that. But But there's no magic. I have that much resources, and I have to choose what I'm going to do with them. What happened in proof of stake? So in proof of stake, we have the same situation, and I ask myself, do I get to build a block now? So do I have a valid proof of stake block? I get a reply immediately. A yes, great, I publish. A no, what do? I have to wait 1 second. And then I get to ask again whether I have a valid block or not. So I wait 1 second, and I try again. But during this second, all of my resources are free to do whatever I want with them. So if a fork arrives, what do? I don't have any resources to hold me back, so I can basically try to extend this other fork as well. Okay? And let's say I find a block for one of those forks. So what will happen? I will publish it, right? But there's a subtlety here. So if you're a rational stakeholder in the system and you propose blocks, and say you find the block for some tip, for some branch of the blockchain, not necessarily the longest one, what is the rational thing for you to do? So the rational thing for you to do would be to publish this block, because maybe there will be a reorg in the future, and maybe all of a sudden this branch will become the longest one, and then you have a block that you receive a reward for. Okay? And since this doesn't cost you anything, because your compute resources are most of the time not doing anything, then you would go ahead and publish this block and see what happens. So what's the result? The result is that both forks would continue to grow. 1 second. And of course, this is very bad, right? Because basically there's no stable state. There's no one blockchain. There are going to be a lot of reorgs all the time. Yeah, so we don't want that. Question?
You said you have to wait 1 second.
Right.
How does the network synchronize the blocks?
So the rate of finding of a miner, of a stakeholder finding a block is, again, it's one per 10 minutes. Okay, once in 10 minutes in average, a stakeholder would find a block and would propose it to the network. So you have a lot of time to to distribute your block. The thing is that you have to wait 1 second for your next attempt at being the leader. So there is a clock in the system. Yes, so the question was, so I said that you have to wait for 1 second before your second attempt, before your next attempt. And he says, who makes sure that you wait 1 second, right? Like who can even check this? So yeah, so let's go back to the formula. So in the formula, you have time in seconds, right? And okay, so say you don't care. You want many attempts. So you don't wait for the clock. You just go boom, like you do with the nonce, and you advance the time in seconds very, very quickly. And then okay, you find that, and then you find a valid block, but the field time in seconds is very, very far away into the future. So if you propose this block to the network, everybody's going to say, wait, my clock doesn't match the time that you wrote here, okay? It doesn't match, so I don't accept your block. Huh? They don't have to match exactly on the second, but they have to be in some reasonable bound, okay? And yeah, this system does rely on clocks being approximately synchronized, probably a bit more than what Bitcoin requires, okay? Yes?
Is the solution to the question that the longest chain means that whoever finds the time in seconds closest into the future, blocking the, if you're more than 10 minutes into the future, you're skipping a block and then you remember the shorter chain, no? So therefore, you only look a certain, 10 minutes into the future, because that's the only time frame from which you could make the longest chain.
I'm not sure I followed, but the point is, it's all very probabilistic, right? So there could be minutes where many blocks are found, and there could be minutes where no blocks are found.
The same logic applies.
Hmm?
The same logic applies that there's a certain time, it's like a half-life in this scenario, that there's a certain amount into the time into the future that it's worth looking ahead because you're probably not going to have somebody else publish a block, and you'll be the longest chain.
Oh, I understand what you say, but let's say you find a block that doesn't extend the longest chain. It's like a fork. You should still publish it, and it doesn't cost you a lot of money to look for this block.
But it's lower value. Lower value.
Yeah, it's lower value, I agree, but since it doesn't cost you a lot of money, then you would probably don't mind, and you would probably do that. Okay, so we talked about the leader election and the randomness problem. We talked about rational forks, nothing at stake. And we're back to the agenda. And we're moving to the challenges. Okay, the challenges in designing proof-of-work systems. And so the first challenge is generating randomness for leader election in a fair way, in a non-manipulable way, in a non-predictable way. And what I'm going to do is I'm going to show you a few techniques of how generating randomness among a set of participants can be done. Okay? Yeah.
You mentioned previously that the timestamp should somehow match between computers, and I guess that all of them will be connected to time servers.
Well, I mean, they can run a local clock. Okay, and they get updated as to the time, to a more accurate time, with every block that they receive. Okay, so if for some reason your clock is very different to other people's clock in terms of how fast it advances, you would be able to kind of, correct it when you get a block. But
it's up to you how to update your clock.
Well, normally nobody would need to update their clock because clocks are usually running pretty. So we assume that the clocks are running pretty closely, like in terms of rate. The rate of my clock and the rate of your clock they're pretty similar. They're running in the same speed. Okay. Yeah.
What is time weight?
Yeah, time weight is just this parameter that says how long does this coin exist. Okay, so if it exists 1 day, if it exists 10 days, 90 days. Okay, it's usually I don't want to get into this, but this is the basic idea. Okay, the age of the coin.
So basically, incentivizes you to put in stake for a longer time.
Right. If you have more coins that have not been spent for a longer time, then you would have more power in the system.
Why do they want to incentivize this?
Well, this actually introduced a lot of problems, and at some point they said, okay, this will be the maximum value of this value will be 90 days. Okay, it does have some problems with it, but at the beginning they thought it would work very well. Okay, we can talk about it a bit later, but it's an interesting question. Okay, let me continue because we have a long way to go, and we are. When did we start? In 8, right? Okay, so yeah, we have to go faster. So generating randomness for leader election. Okay, this is what we're talking about. Solution 1 is called coin tossing. Okay, and coin tossing is a cryptographic protocol, to generate randomness, common randomness between a set of pairwise distrusting people. So I don't trust you, you don't trust me, I don't trust anyone else in this group, and we still want to come up with a way to have a common random string of bits where I feel very safe and I feel very good about the random bits that we got, and I know that nobody manipulated me and nobody tricked me. And this is the main disadvantage, this requires a known list of participants. So this doesn't work with the open membership model of Bitcoin. Okay, it's a very well-known primitive within the cryptographic community. Great. Okay, so let's see how it works really fast. Okay, we have 4 participants. And what do? They each sample, a random local seed, okay? And they get a result. And what they do is they commit to the result. So how do they commit? They can hash, for example, they can hash the random string that they got. So nobody could, right? Nobody knows what is the pre-image of the hash. And what they do next is they share the commitment with all of their friends. Everybody else receives their commitments, and they do the same thing. Okay, everybody shares with everybody their commitments. Great. What I do next, I reveal the actual string of bits that I sampled. Okay? And everybody does the same. So what happens here? I have the commitment, and then I have the random value of everybody, and I can check that it matches. Okay, I can check that nobody fooled me and sent me a random seed that doesn't match his commitment. Once I verify this, we can kind of combine all the random seeds together and make a final random seed for the group. So this is great, but there's a problem. It's called the last actor problem, and let's see what happens. So we're in the reveal stage. Okay, after the commitment, everybody shares their individual random seeds, and then this guy, right? He got all the random seeds from everybody, and he says, okay, what is the final result going to be? So it's going to be this. Do I like this? If he likes it, great. But if he doesn't, then he says to his friends, sorry guys, I deleted my local randomness that I generated by myself. And then what happens? We're stuck, right? The protocol is stuck. We can't do anything. And everybody is very sad. This guy's happy. Okay, so yeah. So what are the possible solutions? So one solution is what Randau is doing. What Randau is basically a smart contract over Ethereum, which says, okay, when you commit to your random value, give me a deposit. Okay, and a deposit in Ether. And if you fail to reveal your commitment, then we are going to split your deposit among the other participants that were honest. Great. Second solution is PVSS. This is a little bit fancier cryptography. And what it does is basically it says, okay, instead of having people reveal their their local randomness, if they fail to do so, we're going to have a cryptographic protocol that will be able, if enough of us cooperate, to open the commitment for you. Okay? And this is done with threshold cryptography. Doesn't matter now. Ouroboros, Cardano, big name, they use it. And we in Orbs, Helix is the name of our consensus protocol, so we use it as well, a variant of it. Great. The disadvantage is that it requires an initial key generation step, okay, which is a step that we do once before the protocol starts. Okay. Back to the agenda. We're done with coin tossing, but let me remind you where we are. We're generating randomness for leader election, and we are moving to cryptographic sortition, yes? In the coin tossing,
yes,
they calculate the random based on the hashes or the original value.
So they calculate the final. So the question was in the coin tossing, when they calculate the final random seed, what is it exactly that they calculate? So yeah, they calculate the original random seeds that people sent them.
So basically, after I send the hash and commit to it, I have to send the original value as well, and then they compare hashes?
They compare, yeah, they verify that what you committed to is the value that you send now. Yeah.
Okay, thank you.
Yep.
Why not just ignore the last actor, the last bad one? Just ignore and take him out, remove him from the game.
Well, because then this guy has basically, okay, so let's say this guy is, he, I don't know, it's not a complicated question, but I don't want to get into this too much. The idea is that this player can now choose between two versions of the randomness that we generate, right? You can choose whether he likes this or he likes the other one. And maybe he's cooperating with other players, and they say, well, you know, we like this version of randomness better. And this could be worse if we have many players are playing and they cooperate, right? So, yeah. Okay, cryptographic sortition. It's the next technique that we'll see for generating randomness. And this is a very, very interesting technique by Silvio Micali. Okay, Silvio Micali, for whoever doesn't know, is a pretty big guy. Gödel Prize, Turing Prize, zero knowledge, invented, you know, zero knowledge. Okay, and he, by the way, he's now on a break from MIT and he's working on Algorand. Okay, so this is suitable for permissionless membership. And the idea is this: we were going to start with an initial random seed. We're going to, you know, just choose a first random seed that everybody feels very good with. Say we choose the hash of the word Bitcoin. Okay, pretty kind of general consensus over this. And then we advance this random seed every round in a semi-deterministic way. Okay, and so we will see that the random seed is advanced in a way that is hard to be manipulated. Okay, and the key feature or the key element that we need for this is what is called unique signatures, unique digital signatures, right? So I have a slide here on digital signatures, but I won't do it. Okay, basically it explains how digital signatures work in a very high level, but you know that already. And so what we will assume is that there is only one signature per message per pair of secret key and public key, okay? So this, for any M, any message, and any secret key and public key with which we sign, we believe, we know, we choose the digital signature scheme such that there will be just only one signature that passes the verification. Okay, great. So we have this initial random seed that we want to advance. How would that work? So we would, every member in our network has a secret key and a public key, and he would check whether he satisfies this formula. Okay? And since the signature is unique, there's only one signature that works, he doesn't have any manipulation that he can do. He either passes or not, but he cannot, you know, try to play with the signature or anything like that. So he checks, and he's sad because he doesn't pass the test, and this one also. And then this one, yeah, he's happy, he passes the test, and we continue, nobody passes the test, and this could be done in a permissionless system, right? And then the guy that was chosen, he is the leader, okay, and he says, I'm going to tell you what the next random seed is, and the next random seed is the signature, again, the unique signature, which he cannot play with, over the previous random seed, hashed. I'm just going to hash that with the round number, doesn't matter, and you get a new random seed. And this random seed, the leader couldn't have manipulated the random seed to his liking, because he must sign with his only signature. He must produce the only signature that he can. Okay, and then we advance the random seed to what this guy says, and we continue. Okay, we do this again and again and again. Great. So it's not that simple, okay? Because what happens if two of the members in our network pass the test, right? And then I'm not going to get into this, but a black box comes. Okay, this is a black box solution, and it solves this with a Byzantine agreement protocol. Okay, so Byzantine agreement protocols, it's a field of research for, I don't know, 30 years. And we use something like that to determine one of those leaders. Basically, it's a communication between all of the participants until they reach a consensus, until they reach an agreement. Who is the leader? Okay, and then there's another small problem that I want to mention. What if? What can happen? Huh? Exactly, nobody shows up, right? So what happens then? Another black box comes, and this black box says, okay, I'll determine the next seed, and the next seed is going to be the hash of the previous seed without a signature, just simply without a signature. The details are quite complicated, but they work with certain assumptions. And yeah, okay? So I don't want to get into this too much, but this generally works. Okay, another thing that improves a little bit on the cryptographic sortition in some sense is the threshold relay service. This is an idea that was developed by Definity. They use BLS signature. They use unique threshold signatures. Again, I don't want to get into this. This is also something that we do in Helix, which is very nice. Okay, and we're moving on to the fourth technique to elect leaders in a fair way. Okay, this will take maybe 5 minutes, and it's interesting, so I'll do it really quickly. So this is a work by Ido Bentov. Ido Bentov is an Israeli guy. He's now in Cornell, I think, in his postdoc. And so he came up with this idea. So he says, we want to choose the leader of the current block, this one, right? We don't know who the leader for this is. So what will we do? We will go to the past, and we'll take m blocks from the past, and we will extract deterministically m bits from these m blocks, okay? And generally, we're going to assume that the leaders that built these blocks, they didn't care. They just built a block and proposed it to the network. So we see these random bits as unbiased. Okay? These are just random bits that are with probability half 1 and probability half 0. And what happens next is we take these m bits and we put them into a low influence function, which I will explain what it is in a second, but basically it's a binary function from m bits to k bits, and k is much smaller than m. And then we have these k bits that should, if the low influence function is good, they should be uniformly distributed. Okay? And then we use this technique, it's called follow the Satoshi. Follow the Satoshi was very popular in the early days of proof of stake. And what it said is just these k bits, there are 2k options there. So let's say there are exactly 2k Satoshis in our system. Satoshi is the smallest unit of currency. So let's see who controls this Satoshi. We follow the transaction graph and we see who controls this Satoshi right now. And the guy that controls this Satoshi right now, he has the right to propose the block. Okay? And so this exactly, this is what Ido Bentov suggests. So what are these low influence functions? What are they doing? So they're supposed to do this thing. So let's say this leader here, this leader here, he is not honest. He's not just going to propose a block, he's going to propose the block that he likes. So this last bit here is not honest. We cannot see it as honest, and we want the influence of this bit to be very, very low. We don't want the last leader here, this one, to have much influence as to the result of which Satoshi is going to be chosen. Okay? So this is the motivation, and let me show you an example of how we can do this, maybe, not that good. So let's take a look at the majority function. Okay, so the majority of, we have 9 bits here, and we select the bit, the majority of bits. Okay, the majority is the output. So what is the probability of this bit, where is it? What is the probability of this bit to influence? the output of the function. So it's a pretty simple calculation, right? There are 8 choose 4 ways to organize the first 8 bits such that there is an equality between among the first 8 bits, and then the 9th bit would determine. And there are 2 to the 8, ordering of 8 bits generally. So if you calculate this, you get 0.273. Great. A better example, and this is a low influence function, is the iterated majority. So in this case, for the last bit to influence, it needs there needs to be a tie between C and D, right? And there needs to be a tie between A and B. Now, what is the probability to have a tie between C and D? Huh? Half, right? Half. And what is the probability to have a tie here? Okay, a majority of unbiased bits are themselves unbiased bits. Okay? So it's also 50%. So what we get is that half times half is a quarter. And a quarter is lower than 0.273. So we managed to lower the influence of the last leader. And this could be repeated. We could build a much higher tree and reduce the influence more and more. And this could be actually done. This could be done even for a set of last bits. Okay, for not just for the last bit, but for a few last bits. And so this is the idea of Ido Bentov. The problem is that it becomes very unpractical if we really want to reduce the influence of the leaders here, and in reality, we're not just going to influence the last bits; we're going to influence all the bits. So it's very hard to construct this to work. Okay, we're done with the first challenge, which was how do we elect a leader in a fair way in proof-of-stake protocols, and we're moving on to the cheap production of blocks. Okay. And so let me just remind you really quickly, we finished the introduction part with this saying, proof of work follows the principle of making history costly to create and rewarding participants that contribute to its majority version. So the whole concept of proof of work is that it's costly to make history. And proof of stake comes and says, no, we want history to be cheap to create. And then what happened? We had the problem of nothing at stake. We had the problem of rational forks that we saw in PPCoin. Okay? So we want to solve this problem somehow, and the idea is quite basic. Who came up with this? Slashing conditions? Vitalik, very good. Okay. And what he says is very simple. He says, this is the idea. He says, okay, history will be cheap to create, but punish economically a miner or a validator or a stakeholder, whatever you call it, that supports conflicting versions of history. Okay? So if you make one history, that's fine. It doesn't cost you anything. But if we find out that you support the 2 versions of history, we're going to punish you. And so how is this going to work? We will define very, very accurate rules or conditions in which you can propose blocks, in which you can vote for blocks and support blocks. Okay? And these rules are going to be detectable such that if you break those rules, you are detected, and we can punish you. And then we will use deposits so that if you are actually caught breaking the rules, we can slash your deposits. Okay? So this is why slashing conditions. Great. And so Casper, the Casper team were the first to, I think, to propose these ideas. And Tendermint, which is another interesting protocol, proof-of-stake protocol, he talks about, how to do this in a specific protocol. Okay, so we're great. We solved the problem, right? Yep.
Competing histories are per miner, right? Not on a blockchain level.
Yeah, per miner, we have rules. If you break them, you're punished.
So a miner cannot support 2 conflicting histories, not that it is compared other from the...
Right, right. It's on a minor base. It's on a per miner basis, per validator basis. Okay, so we solved the problem, right? We will use deposits and slashing conditions. Everything's great. But wait, not so fast because, okay, so they make a deposit, and now they can vote for histories, and they can support histories. That's great. But at some point, they're going to want to withdraw their deposits, right? And then what happens? Then they can still propose another version of history, but then we don't have the deposits to punish them if they, right? If they do it, they don't do it honestly. So again, let me make this clear. They deposit, they withdraw their deposit, but the blocks that they created or they voted for, when they did have that deposit, they still exist. So they could go back to those blocks, and instead of the block that they proposed in the first time, they would propose a different block. And since they already extracted their deposit, there's nothing we can do. Okay? And this is why we call long-range attacks, because these attacks have to go a little bit back more into the past. And this is you know, what I just mentioned here. Okay, so back to the agenda. What we're talking about, okay? Let me put you in context. So we were talking about the problem of chip production of blocks. We said, oh, there are slashing conditions. We solved the problem. But then we got back to square one because we said, oh, eventually they will have to take their deposits out. And we said, okay, this is called long-range attacks. Okay, and what I'm going to do now, I'm going to propose 3 ways to kind of mitigate this problem. Once again, these are not really solutions, but these are ways to make the system live with this problem. This problem is very inherent. It's very hard to solve, but we want ways to make it less severe, okay? And to convince ourselves that the system could still work even though we have that problem, okay? So, solution 1, weak subjectivity. Okay, so what we do here, we say there's going to be a withdrawal cooldown period. So say our attacker, she had a deposit, she voted for blocks, and now she wants her money back, and she asks for a withdrawal. What we'll tell her? We'll tell her, okay, but you have to wait for, say, 4 months before you get your money back. So in these 4 months, you cannot vote, you cannot play, you don't participate in the game, but you still don't have your money, and it's still in a deposit, okay? And then, after these 4 months pass, she takes her money back, and she wants to try to build an alternative history. So she has to go back 4 months in time in order to propose a valid block that anyone would care about, right? Because in these last 4 months, she wasn't allowed to vote in our blockchain, yeah? Okay, so she goes back 4 months and she starts a reorg. She starts a really long reorg of 4 months, but you know, it doesn't cost her anything, she can do it, right? Because we said history is cheap to write. But we know that for a fact. We know that if she would try an attack, it would have to be at least 4 months old. And now we tell our users, listen, users, please log on periodically. And at least once in every 4 months, so that if you see this really long reorg all of a sudden of 4 months, you will know to reject it. You will know that it's an attacking chain, okay? So the problems is not so much with the users that log on that are kept, that are connected to the network all the time. The problem is more with other users that log off for very long periods of time, or for new users that join the system, and they can be presented an alternative chain, and it would be very hard for them to know to distinguish between two blockchains, right? Two histories. So in proof of work is objective in this sense, because if you're presented to two valid histories, you can choose the right one, you can choose the majority one, right? How do you do that? Yeah, where there is more cumulative work done. So here it's subjective in a sense, because if you come and you log on after a very long time and you're presented to histories, there is no way that your client, on your laptop, would be able to detect which one is the right chain. Okay, and so it's called weak subjectivity, because you would have to kind of rely on the social layer of consensus. You would have to go and check in a block explorer that you trust. Am I getting the right chain? Or you maybe ask, a reputable member of the community, is this the valid chain? So it's not something that's done on your computer. So this is why it's called weak subjectivity. The second thing is tapos. Tapos, yeah, you are all with me? All is good? Yep. Yep.
I guess that there is also the possibility in weak subjectively that few parties can cooperate, like with intervals of 1 week for asking their money, and that way to cooperate for a set of blocks that they can all fake, let's say. So if I have to wait for a month, so I can cooperate with you, and we will ask our money with intervals of 2 months, and then we can both together think of blocks.
So I assume that when you, I assume that you have enough power to build blocks on your own. I give you more power than you probably have. Okay, you're a single attacker or you're a bunch of attackers that are colluding. For me, it's the same. You are able, I'm assuming that you are able somehow to build a very long reorg of 4 months. So and this in practice it would be hard to do, and it would, as you say, you would have to cooperate with other people that have stake in the system in order to have enough power to build blocks. Okay, but yeah. Okay. So another solution to the long-range attack, tapos. Okay, tapos stands for transactions as proof of stake. This is by Dan Larimer. Dan Larimer, the EOS guy. Okay, just launched EOS. Yeah. Okay, so what does Dan Larimer suggest? He says, take all the transactions and add a little feature to them. Every transaction here would include a hash of a recent block when it was issued. Okay, so when the guy that issued TX2, he knew of this block. Okay, so he could include the hash of this block into this transaction. Very simple. Okay, and now our attacker comes and he wants to build an attacking chain. So he starts building his chain, great, and he wants to include transactions in his blockchain, right? So he goes to the main blockchain and he says, okay, can I take TX1 and add it in my block? And the answer is yes, because the block that TX1 refers to is still in this branch. However, when you go to TX2, you cannot include it, okay? You cannot, wait, yeah, he's trying to put TX2, but he's sad because he cannot include TX2 because TX2 points at this block, and this block is not in the branch that he's building, okay? So there are many transactions that he cannot include. And then what we need is some way to determine which chain we like more according to the transactions in each branch. Okay, for example, what we could do, we could say, okay, choose the branch where more fees were paid. Okay? Because probably this is the honest chain, right? Okay. Okay. So this is transactions as proof of stake. And now, ephemeral keys. Okay, I think.
What makes it an honest or dishonest?
Yeah, so it's a good question. Yeah, so so we would want some criteria that is hard to forge. Okay, for example, fees are not that good because the attacker can control. He is probably the miner of these blocks, so he basically is paying the fees to himself. So he could. It could look like he could include fake other transactions into his blockchain, paying to himself, and he could have a fee paying to himself. So this is not a very good criterion. But so what Dan Larimer originally said, he would say, let's check in which blockchain there is more coinage being consumed, because if you're an attacker and you don't control much of the money, let's say you control only, I don't know, a half of the money, okay, which is a lot, right? Well, if you control half of the money, it doesn't work. But if you control, let's say, a little bit less than half of the money, then what happens is that in this fork, only there is half of the money, more than half of the money that is frozen. It doesn't move because you don't have the private keys to create transactions for these UTXOs, right? And so if you look at the long run, then probably less time, there's going to be less time consumption of coins in this fork, okay? And then you could kind of compare and select the right chain. Okay. Back to the agenda. We are in ephemeral keys, and I'm not going to talk about ephemeral keys because it takes a few minutes and we don't have them. I want to go to Ethereum. So blah, 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 blah. Okay, great. Casper FFG. Okay. So what is Casper FFG? So FFG stands for Friendly Finality Gadget. Okay, finality, I'm going to say this word a few times now, so get used to it. Okay, in very general terms, Casper FFG is a proof-of-stake layer on top of the existing proof-of-work chain, proof-of-work Ethereum chain, that's supposed to give us what they call economic finality, okay? And I'm going to explain this in a second, but if we erase the word economic, then the idea is pretty clear. We want finality, meaning we want to know once a block is final, we want to be sure that it will stay in the canonical chain forever and ever, okay? So this is the goal. And we know that this doesn't work in proof of work, okay? So in Casper FFG, there are validators, as we said. There are deposits. In order to become a validator in Casper FFG, you need to deposit Ether into a smart contract. How much, you know? Huh? Okay, so 32 Ether. There's a big debate about this, okay? In some of the approaches say 1,500 Ether. Okay, some say 32, so we don't know what's going to happen. There is going to be votes. So you vote for blocks that you like, that you want to finalize as a validator, and there are slashing conditions. So if you violate the slashing conditions, your deposit is slashed. Okay, and the idea is to reach economic finality. The idea is that we cannot promise that there's finality, right? I mean, this is something that is, we cannot say how people will act. They might break the rules, they might not break the rules. We cannot guarantee finality per se. But what we can do is we can guarantee economic finality. So what it means is that, and I'm going to go over the formal definition in a second, but the idea is that we want to know how much money exactly it would cost to do an attack on this blockchain. So for example, in Bitcoin, we can estimate, okay, we said you need about 2.5 million ASICs, and we can kind of estimate how much electricity is being consumed in Bitcoin, and we know that the price is very expensive. However, if I'm very smart and I find a really good ASIC, then I might, and I don't tell anybody, then I might, you know, I might win and I might attack the blockchain, the Bitcoin blockchain successfully. So we want to know, we want to have an economic, an explicit cost of attack, okay? And so the other motivation is that, you know, Ethereum is a very big blockchain. Its value is I don't know, $60 billion now, and they're talking seriously about transitioning to proof of stake, like removing proof of work altogether. But doing such a move, you know, fast is very, very dangerous. And if there's a bug, if there's a mistake, if proof of stake turns out to be not that secure, then we have a big, big problem. Many, many people will lose a lot of money, right? So they want to do it gradually, and this is exactly what this Casper FFG comes to do, to come as a second layer on top of proof of work to kind of check that proof of stake is secure enough. The second thing is that there are advantages in terms of scalability in many aspects in Ethereum that they hope to achieve with this. So what do we have currently in Ethereum? Currently, we have only proof of work, so if miners working, they follow the longest chain rule, and reorgs can happen. So this is the longest chain for now, and then this block comes, and this is the longest chain for now. And then this blockchain comes, and it's not the longest chain, so we don't put it in red. But then, okay, a block that used to be in the canonical history is no longer in the canonical history because there was a reorg, and this happens again, maybe, right? Okay, so we don't want that. This is exactly what we don't want. So the future, we will have proof of stake finality. So what we will have miners mining. We will have validators that are bonded, they have deposits, vote in order to finalize blocks. And the miners would have to kind of forget about the longest chain rule that they know, and they would have to adopt this new rule that would tell them to keep working on the finalized chain. Okay, so let's look at that. We have a block. It's not finalized yet. We have another block. This is currently the longest chain, but it's not finalized. And only now, once this block has accumulated enough votes, does it become finalized, okay? Proof of stake votes. This block comes, it's not finalized, not final. Okay, longest chain, but it's not final. And then all of a sudden, for some reason, validators, the proof of stake validators, they like this block, and they finalize this block. Okay? And so now the miners have to forget about the longest chain rule, and they have to start building on this branch. And once they do, this block would get finalized, but we won't have a reorg. Okay? No reorgs. So let me rephrase the main goal again concisely. So Casper is designed to satisfy the following properties. We want accountable safety. We want plausible liveness with economic finality. And I'm going to break down these terms one by one. So what is economic finality? A block B is economically finalized with security margin X if a client has proof that either, okay, one option, either B is going to be part of the canonical chain forever. That's what we really want. That's finality. But we can't have that. So there's an OR. The OR says that the actors that caused B to get reverted are guaranteed to be economically penalized by an amount equal to at least X dollars. So if it was to be reverted, this finalized block, somebody is going to pay a lot of money. Okay? This is the idea of economic finality. What is accountable safety? And so I start with defining it in regards to finality, to actual finality. So we say two conflicting blocks, B1 and B2, cannot both be finalized. That's what we really want. Okay? We want them not to ever be finalized together if they're conflicting. But we can't have that. So we have accountable safety with economic finality, which means that two conflicting blocks, B1 and B2, cannot both be finalized without a violation of the slashing condition and the misbehaving actors being slashed. Okay? So this is, if there are two blocks that are conflicting and they're finalized, then we will detect those malicious actors and we will punish them. Liveness. What is liveness? So liveness means progress. The protocol keeps advancing and keeps finalizing blocks. So new votes can always be cast such that new blocks get finalized. Great. We want that, but we want that even better. We want that without any validator having to break any slashing condition. So we want the slashing conditions to be not that severe so that they will allow the protocol to continue. And we want plausible liveness, which means we want that provided the block producing service, the block producing service are the miners, the Ethereum miners, they keep extending the correct chain. And the correct chain, we'll define it later, but it's not the longest chain. Okay, so the main goal, again, is that we have accountable safety, we have plausible liveness, and we have economic finality with X, where X is third of the total deposited funds. So if you see in the, if you see in the Casper smart contract, if you see, I don't know, 3 million, Ether in the value of $3 million, then you know that if there was to be a reorg, somebody is going to lose $1 million. So if you have small transactions that you want to do and you want to receive, you would say, okay, you would feel probably pretty safe. But if you have a very big transaction, then you might say, well, maybe I should be a little bit worried. Okay, but the idea is that we will have a tremendous amount of money here. Like maybe if the Ethereum network is 60 billion, is worth 60 billion, maybe we would have, I don't know, $10 billion there. So everybody would feel very safe to transact, okay?
You don't really know if it's going to work. And even if it does, obviously, the value of your holdings, you mind that now you control the chain, you control a substantially lower chain in value because the value of the coin would go down drastically. So what's the difference?
Yeah, so I agree. I agree. The main difference is that the cost is explicit for an attack. So I don't know, think about it.
If it's explicit, it's even worse. Because you can actually set a price tag on your actions, and if you, under proof of work, there is no price tag. It could be even far, far greater than what you do.
Well, the thing is the following. With mining, as we said earlier, if someone in this world somehow manages to design a miner that is much stronger than anything out there, and this has happened in the past, right? The Ant miner surpassed any other miners in the market by a lot. And the manufacturer of this miner could have said, well, this is my miner. I'm not going to tell anybody about this miner. And I'm going to manufacture, I don't know, a bunch of those, and I'm going to mine on my own. And then what happens is either he is gaining control over the network and nobody knows, which might be the case of Bitcoin. We might don't know that, but we might have maybe a single miner mining Bitcoin right now that's surpassing all the others. So this is a risk that you have, right? Because you don't know. Mining is a game. Maybe you find a loophole there. Maybe you find a way to calculate those hashes faster than the other people. And then all of a sudden, this crazy amount of terahashes of proof of work that's being done means nothing, because I somehow managed to get a huge advantage. But with an explicit cost, then you would have to get those Ethereum tokens, these Ether, and you would have to buy them somehow. So unless you're, people say, but hey, what if I'm in the system from the very beginning, and in the beginning there's a really bad distribution, and I control, 1 or 2% of the coin, or even more, and then I have a huge amount of power in the system. That's also right. And then the explicit cost of attack is tricky, because if I already have these, huge amount of coins, then I don't really have to buy them. So there are disadvantages to here and there, but I think this is kind of a proof of concept thing. What Ethereum is trying to do is a proof of concept. They're trying to show that proof of stake could work, and that people would follow it. People would put money into the smart contract. They would vote. There would be a very nice distribution. There could be probably better analysis done over how distributed the network is, like how many different entities are actually being validators. Yeah, so I don't know. It's complicated, but that's what they're doing. So I'm just here to. What do you mean? Right.
So somebody locked in all his money somewhere and he lost it in some kind of DAO scam of some sort. Mm-hmm. Who knows what it was? But if the cost of attacking that and putting that money back where it was originally is, say, $30 million, and he lost 150 in the deal, would then this not be a temptation to use some kind of democratic process to fix problems and, bail people out?
So I'm not talking about governance here at all.
But in the instance that you purposefully pull off a reorg, accept the slash in order to give somebody back his 100 million.
Yeah. So you would have to convince miners, right, to reorg, and you would have to convince the validators. So this problem becomes even more harder now. If you want to do it like this reorg, I think it makes things even more complicated. Okay, so this is the main goal. Okay, let's get back to the thing. I finish in a few moments. Accountable safety, plausible liveness with economic finality X of 1/3 of the total deposited funds. Great. So let me first show you why this is not that easy to implement. Okay. So if you are to design such a thing, you have to tell me two things. You have to tell me what is a finalized block, right? When does a block become finalized? And you have to tell me the rules, the slashing rules, under which people get slashed. So the finalization criterion for my attempt here, that's not going to work, is the genesis is finalized. Okay, I assume that the genesis is finalized, and then every block is finalized if 2/3 of the validators voted for it. So votes would be cast for blocks, and if a block gets 2/3 of the validators, and validators is not validators, it's the accumulated Ether value that they have, would have to be 2/3 of the total deposited amount, then this block is finalized. Great. And there are two slashing conditions in this algorithm. A vote to finalize a block will result in slashing if it is not a descendant of a finalized block. So you cannot vote to finalize a block unless its ancestor is already finalized. Okay? And then voting to finalize two distinct blocks at the same height, so if these two distinct blocks are at the same height, then you will be slashed. Okay? You cannot vote for two conflicting blocks in the same height. Okay? So let's see what happens with this algorithm. It's safe, right? Because if I have a finalized block and there is a candidate block and 2/3 of the votes are cast for this block, then it's finalized, right? We have a finalized block. And then another candidate block comes, and it gets also 2/3 of the votes, and then it becomes finalized. Then what would happen? Slashing, right? At least third had to vote for both of the blocks, and then a third would be slashed. So this is not a formal proof, but I can tell you that this protocol is safe. Is safe under the economic finality condition that we said. But it's not live, okay? This is the main problem here, because why? Say we have half of the validators vote for this block, and then another half vote for this block. What would happen next? Nobody, I mean, none of these blocks could be finalized because none of these blocks could get 2/3 of the votes without people being slashed. Okay? So this gets us stuck. So this is not good. Okay? Network is stuck. Great. So Casper. We're actually getting into the details of Casper now. It's not very complicated, but this is Casper. So a vote in Casper is not, you don't vote for a block, you vote for a link between two blocks, a source block and a target block, okay, S and T, and you include their heights. And the validator is V, and you sign all this and you send it to the network, great. So why do we use heights? Why do we need to use the heights there? This is for violation proofs, right? If somebody violates our rules that we will see in a second, we want to be able to prove this, and we will need these height fields. But I'm not getting into this now. I can, if you want, I can explain more in a second. Why links? Why not vote for blocks? So this is not a must. Hot Stuff, which is a protocol by VMware Research, suggests a a variant of Casper, basically, that in which votes are cast for blocks and not for links. So it's not it's not very critical, but this is how Casper is done. By the way, I have to say this: there are a lot of versions of Casper out there because this is an evolving project and it changes often. But this is the latest. This is the latest version of it, and there's a link to the source, the white paper where they present this algorithm. Okay, so in order to understand when a block is finalized, I have to define what is a supermajority link. Supermajority link is a link between two blocks, S and T, where 2/3 of the validators vote for. Okay? Yeah, at least 2/3 of validators vote for. What is a justified block? Okay, justified block. So we say the genesis is a justified block. And in addition, if there is a supermajority link between S and T, and S is justified, then T is also justified. I will show that in a figure in a second, but try to get this. And then finalized block. So if ST is a supermajority link, okay, meaning it got 2/3 of the votes or more, and S is justified, and the height of T is the height of S plus 1, then S is finalized. Okay, so let's look at this in this drawing. So R is justified because it's the genesis. Great. And then there's a supermajority link from R to B1. This makes B1 justified. And then since B1 is, the height of B1 is 1 more than the height of R, then it makes R finalized. So R is a finalized block, okay? It should never be reverted. And then we have a supermajority link from B1 to B2. So B2 is justified, but it's not yet finalized. And then we have, why is B1 not finalized at this point? Because the height of B2 is 2 plus the height of B1. It's not 1 plus the height of B1. Okay, so B1 is not finalized yet. And then B3 becomes justified. And then B4 becomes justified. And what happens to B3 now? It's finalized, right? And then all of the blocks that are the descendants of, or the ancestors of B3, they are also finalized. Okay? So now this chain should never be reverted somehow. Great. So what are the slashing conditions of Casper? There are 2. In some versions there are 4, but in this version there are 2. So you are a validator. You want to cast votes in the protocol, and you made this vote. Okay, from this block to this block, great. Now you cannot cast this vote. Why? Because the h of your first vote, the height of the target block in the first block and the height of the target block in the second vote is the same. Okay, so a validator must not publish 2 distinct votes for the same target height. Great. Slashed. Okay. The second slashing condition is the following. You cannot, a validator must not vote within the span of its other vote. So you're a validator, you come, you cast this vote, okay? Then you're not allowed to cast this vote. Okay? If you do that, you're slashed. Great. So what am I to show you now? I want to show you, let's play this game a little bit. So I'm going to pick a block here, and I'm going to ask you, can it be justified? And you'll tell me. So what about this block? Can it be justified without breaking? Can it be justified without invoking any slashing conditions? Into the next height, but not into a similar height. No, so not the span. The span we don't cover because they're all what do you say? Ishivyanot chazakim. They're all yeah, strong inequalities. If it was katan shaveh, then then we had a problem. Right, right. So surprisingly, this block can still be justified, and then it would make this block finalized, right? Let's check another one. What about this one? This one, no, right? Which slashing condition? Yeah, but which slashing condition do we break? The first one, right? The first one. So this is bad. We can't do this. This will never be justified. Okay. This one can be justified. Great. And then this one can be justified. Great. Okay. And this would. This one? Yeah. This? Still not possible.
Why would you want a system where that one is possible to justify if he has no, if his descendants?
Well, this is probably not something that you want, but this is a byproduct of the protocol. It's true that
finalized, not justified.
Exactly. You care about finalized. You care about finalized blocks, not about justified blocks. Justified blocks are just a means to get to the finalized blocks, but you care about finalized blocks. Okay.
Publish those. Let's say the 3 things on the left side above the one to the left of B2.
Right.
So B2 star, let's call it.
B2 is here.
B2 star is the one to the left of him. Directly left of him in the same height.
This one? Oh, this one?
Exactly. He cannot be justified, we say.
Right.
If we didn't have any children from him yet, the 3 ones that are his children, you would have an incentive to publish those in order to get something that's possible to justify in order to finalize that block.
Yeah, right. So if you were a miner, and for some reason you want this branch to be finalized, but you don't like this branch so much. You prefer this branch. So yeah, you would have to keep proposing blocks on this branch, and this branch can still, at this point, it can still be the finalized branch, okay? Because you know, a really high block here can be justified, and then the following one would be finalized, and it would finalize the whole branch. Right, exactly. The higher height, yeah. Yep.
A pool of validators that reaches a 33% threshold controls the network.
Okay, so they don't control the network, but they can freeze the network, right? If they don't vote.
Yeah, that's what I mean, like extortion the network to abide to the rules.
That's a great question. I'm going to answer it in a second, okay? I'm going to answer it in a second. So now I was supposed to show you the proofs, right? We said we wanted safety, we wanted liveness in terms of economic finality. So I was supposed to show you these proofs now, but we're really late, so I'm just going to skip this. And let me just show you this slide really quickly. So the idea here is that I kind of cheated when I explained Casper. In Casper, you don't really vote for links between blocks. You vote on links between checkpoints. And what is a checkpoint? A checkpoint is a block, only it is a block whose multiple is 100. So either the genesis, whose height is 0, or something of the height of 100, something of the height of 200. These are checkpoints. And you vote for links between those checkpoints. So for example, if you are a validator and you wanted to vote for the link between this block, this checkpoint, and this checkpoint, you would have to do it after this block is published, meaning in this epoch. An epoch is the time between two checkpoints. And you would be able to vote for this link with h of s equals 0 and h of t equals 1. Okay? And you would do that as a regular Ethereum transaction that would go to the Casper smart contract, and the smart contract would keep track of all these votes and would say which blocks are justified, which are finalized, etc. Great. Okay, so all of this is done, and then for your question, this is really the last slide. So first of all, we said we want people not to cheat. We want to have explicit economic finality. So we disinvited breaking the rules by saying, okay, if you break the rules, we will detect you, and we will publish a violation proof, and we will slash your deposit. And this is all done automatically in the smart contract. Nobody does this manually, okay? Great. And then, in order for these 33% of the stakeholders not to be able to freeze our blockchain, we encourage participation. How? We slowly drain your deposits if you don't vote. So if you don't vote for some reason, we will drain your deposit until, if you had 33% in the beginning, you would have less and less, and the other participants would be able to finalizing blocks. You get drained over any branch that you don't participate in, right? So if you're at 33% and you're working on your own private branch, first of all, you won't be able to finalize any blocks, right? But nobody cares about your branch. And in the actual branch people care about, and that miners continue working on, you would be drained. On branches that you don't vote, you can't be drained, right? Okay, we don't want that to happen too often, because maybe you're an honest validator that you follow this branch for a second and not another branch. But if you keep not voting on a specific branch, on this branch, you could be drained. It doesn't matter what you do on the other branches, right? They're all different branches. So there are the smart contract which different states. 1 second, let me just, final line here. What we see until now is that we are only, who would participate in such a protocol where you can only lose money? You can lose money if you violate the slashing condition, you can lose money if you don't participate. Why would I participate? You would participate because there is also an incentive here, which is an interest rate that you get on your deposit. Okay? And there is a lot of talks of how to do this correctly, but we're talking about 1 to 2% annually of interest rate. So it's not as exciting as miners, right? Miners get much more, but you don't do anything, right? You just vote once in every 100 blocks, and you get 1 or 2%, so not that bad. The question was, how do the validators know which blocks they should follow? Great. So if you were an honest validator, you would probably vote on the first checkpoint that you hear. Okay, if you hear of a specific block, of a specific checkpoint, then you would go ahead and vote for it. You wouldn't wait. However, if you were a little bit suspicious, what you could do is you could say, okay, I'll wait a little bit. I have 100 blocks now. I would wait. I would see that this block, this checkpoint gets enough support from the validators, and only then I would vote. If you work correctly, then nothing should happen to you. It's not that blocks are being found that fast. And I mean, yes, Ethereum are talking about making the block rate much faster with this, because the risk of forks would be much smaller in a sense. Miners are going to oppose this because it's going to mean that many of their blocks are going to be wasted and they're not going to get a reward for. But yeah, I mean, as a validator, you want a very good connection to the network, just as miners want, because miners, if they are in a distinct part of the world, if they're distant from the rest of the network, then they lose because it takes about 15 seconds to find a block in Ethereum. If it takes you 3 or 4 seconds more to get the block, then you have practically no chance of getting it or finding any block. So miners and validators in general, they all want a very good connection. So this risk is theoretical mostly. But yeah, I mean, it's there. It's there, and validators will need very quick connections. Let us, I think that we need to finish because we're 20 minutes late, so we can talk offline. Yeah.
Thank you very much, David.